Okay, so as we are looking at today, we are going to be doing what's called inverse functions. Inverse functions are created by switching your x and y values, or your x and y coordinates. It's a function from set B to A, written as, and here's the key, it is written as f, and then you have this -1 that looks like it's in the exponent. If that's not super clear, just look down here, that's what it's going to look like. The key is that an inverse function still is a function. Okay, it's going to hold all those properties of functions that we've already looked at. So the way that you would read this, or the way that you're going to hear us refer to this f of -1, or f to the -1, that is either f inverse, or the way that I read it more frequently is the inverse of f. Okay? Now, if you think about this logically, the next piece makes sense, because if you are switching your x and your y values to go from your original function to your inverse, not only are your x's and y's switching, but so are your domain and range, because the domain is connected to your original x, and your range is connected to your original y. So if your x's and y switch, so are your domains and ranges. So your domain of your f is equal to your range of your inverse. And the same is true the opposite way. The range of your original is equal to the domain of your inverse. So since your x's and y switch, so do your domain and range. The last piece here, this is going to be used to verify that what we are coming up with is indeed an inverse function. And so the key is that the inverse functions undo each other. In other words, when you do the composition, the composite of those, so you plug in your original f function into the inverse, or you plug the inverse into your original f, either way, you're going to get what's called the identity function. And all that means is that when you do the composite, they are both going to simplify to equal x. Okay? So what we're going to do is we're going to do a couple examples that are fairly basic to start, and then we're going to work to get a little bit more difficult. Okay? So when you look at the examples and it says find the inverse function of f of x equals x minus 6. Reminder, f of x is like y. Okay, so kind of think of it like this. The very first step that you're going to do is you want to rewrite the equation with your x and your y switched. So if we look at our original, it becomes x equals y minus 6. The next step that you're going to do is you're going to solve the equation for y. Once you do so, that is considered your inverse function. Okay, so if we rewrite this one, we're going to go ahead and add 6 to each side. So we get x plus 6 equals y. Again, this is now our inverse function. So we could say that x plus 6 is equal to the inverse of f. Okay, now notice that it also says to verify that those composites are equal to the identity function. In other words, they equal x. So your step 3 is that you need to find f of the inverse of x. So in other words, you're going to plug in the inverse into your original equation. So we would take this equation up here and what you just came up with here, and you're going to use those as composites of each other. So in other words, I'm going to plug in my inverse, I'm going to plug in parentheses, and then minus 6, that's part of the original, which will then simplify to be x. So we're good. And then I would do the same. I'm going to plug in my original, x minus 6. Okay, I'm going to take and plug it into my inverse function. So my inverse function we had was x plus 6, and we're going to plug in the inverse, or excuse me, the original, x minus 6. When I were to simplify that, that does equal x, so we're good to go. And it makes sense logically with this simplified version. If you look at x minus 6, the opposite of subtracting 6 is adding 6. It makes sense that those two functions will undo each other, that one is minus, one is addition, so it makes sense. Okay, think about your math making sense. So the second one, find the inverse function of f of x equals x plus 7. Again, this is a fairly basic one. When you look at this, the very first thing you want to do is you want to go ahead and switch out your x's and y's. So you get x equals y plus 7. And then you want to go ahead and subtract your 7 from each side. So x minus 7 is the inverse function. And that's our first step. Notice that it does ask us to verify. So when we go to verify, we can do f of the inverse. And so again, we're going to plug the inverse into my original equation. So my original equation was x minus 7. I can plug it in, excuse me, x plus 7 was my original. I can plug in my inverse, x minus 7, and that equals x, so it checks. I would also want to plug it in the other way. So I want to plug in my original into my inverse. So my inverse function is x minus 7, and my original function was x plus 7. So again, those will check. Okay, the next one is similar in concept. The only difference is it's y equals 4x instead of addition or subtraction. So again, if we follow our steps, we have y equals 4x. So when I swap out my values, I get x equals 4y. When I solve for y, I end up with x over 4, and then that's going to be my inverse function. So that's my function, and then I'm needing to verify those composites. So again, I'm going to take and I'm going to plug in my inverse into my original equation. So if I do that, my original equation was 4 times x, but now my inverse is x over 4. So that does equal x, and it checks. And then I'm going to go the other way. So I'm going to plug in my original into my inverse. So if I look at my inverse, I have x over 4, but again, my original was 4 times x. That will simplify to be x. So in both cases, it does simplify to be the identity function, so those are indeed the inverses. So now once we look at these, this gets a little more complicated, because this makes sense that if my original was subtraction, my inverse would be addition. Same thing with the second thing. If my original was addition, my inverse would be subtraction. Same thing with the last one. If my original is multiplication, my inverse would be division. The problem is they're not always that easy. If you look at the next example, we have find the inverse function of f of x equals 5 minus 3x over 2. We're going to follow our exact same steps. We're going to swap out our x and y. So the first thing we want to do is make this x equals 5 minus 3y over 2. So our first step is to multiply each side by 2. So we get 2x equals 5 minus 3y. And to keep solving, I'm going to subtract 5 from each side. And then I want to divide each side by negative 3. So when I do that, that's going to be my inverse function. Okay, so my inverse function is going to be 2x minus 5 over negative 3. So the next piece is to verify that they are indeed inverses. So the first thing I'm going to do is I'm going to plug in that inverse into my original equation. So my original is 5 minus 3. I'm going to put this whole thing in parentheses over 2. The whole thing, the inverse that we had was 2x minus 5 over negative 3. Now be careful with your negatives. All right, so when you look at this, it's pretty easy for most of us to see that the 3 on the outside here will cancel the 3 on the bottom here. But remember, a negative and a negative will turn into a positive. So that's going to turn into like a +1 you can think of, or if you just want to ignore the 1, that's fine. But the reason that sign changes is because we have a negative and a negative, and then your 3's cancel. That's still all over 2. That 2 has not gone away. So if we simplify our numerator, at this point, we have a 5 and a negative 5, which will cancel. So we have 2x over 2, which will simplify to be x. So we have verified it one direction. Then we need to go ahead and verify it the other direction. So if you have f of x and you're plugging it into your inverse. So we look at our inverse that we have here on the left. We can go ahead and do some substitutions. We have 2, and then I'm going to put some parentheses here, and minus 5 all over negative 3. And if we substitute our original was 5 minus 3x over 2. Okay? So again, our 2's cancel, so we're left with 5 minus 3x minus 5 all over negative 3. Our 5's will cancel, so we're left with negative 3x over negative 3, which then simplifies to be x. So we actually have gone ahead and verified in both cases that our original inverse that we came up with here is indeed our inverse that we need for our final answer. Okay? All right, let's look at one more that's a little bit, again, it's not as cut and dry as the previous ones where it's just addition, subtraction, multiplication. So our first step is to go ahead and swap out our x's and y's. And now we have to solve for that y. So to get rid of the square root, we need to square each side. So we get x squared equals, all that's doing is canceling out that square root. Add our 3, so we have x squared plus 3, divide by 2. So at this point, we have x squared plus 3 divided by 2 is equal to our inverse function. Okay, so far this is our inverse. Now what we need to do is go ahead and verify those. So we would take our inverse and we would plug it into our original. So our original was 2, and then we had 2x minus 3, square root of all of that. We would plug in our inverse, which we had was x squared plus 3 over 2. When we go to simplify, our 2's will cancel, so we're left with x squared plus 3 minus 3. Again, our 3's obviously cancel, and the square root undoes the square, so we have verified it one direction. Now we need to go ahead and plug in our original into our inverse. Okay, so our original, if we look at our inverse, we have x squared plus 3 over 2. When we plug in our original, we get 2x minus, or the square root of 2x minus 3. The square and the square root cancel, so we're left with 2x minus 3 plus 3 all over 2. The 3's cancel, and so do the 2's. So we have verified that it works both directions. Okay, so that is how you would go ahead and write an inverse function and then also verify that they are indeed inverses. Okay, so let's talk about the graphs for just a minute. So because the inverse means to switch your x and your y, the graph of a function and its inverse, those are a reflection. They're a reflection over the line y equals x. Okay, so if you think about this, if you notice this picture, any point that you pick on your original function, when you reflect it over that y equals x, all you're doing is swapping out your x and y values. Okay? So in other words, that x equals y line, this line you see in the dotted here, that becomes a line of reflection or a line of symmetry between your original function and your inverse function. Okay? So when you see this next part, when it says verify that f of x equals 2x cubed minus 1, and then you see this g of x, the cube root of x plus 1 over 2, are inverse functions of each other. Notice it says graphically. So we've already done algebraically where you substitute one function into the other and vice versa. But graphically, all that's asking you to do is, let me go ahead and just sketch a picture. So if you were to get on your graphing calculator or Desmos, either one, your original function, so f of x, is going to look something like this. Okay, so it's been shifted down one unit. It's your cubic function, so it kind of looks something like this. Again, you go to Desmos or your graphing calculator and type that in. You're going to see something similar to that. The key is here, we have 0, negative 1. Keep in mind, if it's the inverse function, you are flipping this. So what was once 0, negative 1 in your inverse function is going to be negative 1, 0. And then again, when you have 1, 1 here in your original, it's going to look something like this. And so now when you finish graphing this, it's going to look something like that. And the reason that this works, or that you can verify it graphically, is if I were to look at this y equals x line that I just attempted to do in purple, but it turned red, those are reflection graphs of each other. So every xy that you see in the original becomes your yx in the other. Okay, your x's and y's just flip. So whenever it says to verify graphically, that's what it's referencing. They want you to look at the graph and see that it is a reflection of each other. The only other piece to be mindful of is originally, when you are testing to see if a function is indeed a function, you use what's called the vertical line test, meaning you draw your line in vertically and it cannot have more than one intersection with any vertical line. The horizontal line test, let me go ahead and write this out and then we'll go ahead and explain it for you. So the first thing is the inverse of a relation. The inverse of a relation is a a function if and only if each horizontal line intersects the graph of the original in at most one point. Okay, so let's look at this graph over here. Okay, so notice it says using the horizontal line test, determine if the following functions inverses are functions. So right now, what you see in this first one, you see a parabola. This original is a function. Now, if you were to take and go ahead and do the inverse, okay, you could see something like this. Boop, it's gonna look like that. Now, if the parabola looks like that, obviously it's not a function because it would fail the vertical line test. So what the horizontal line test allows for you to do is it allows for you to totally forget about doing the inverse first. It's just gonna say if your original fails this horizontal line test, that means your inverse will fail the vertical. It's just taking a shortcut. It's saying if it doesn't work, the horizontal doesn't work in the original, it won't pass the vertical line test for the inverse. So in other words, the inverse, not a function. Okay, whereas if I look at this line, I could draw this, only intersects once. And here we have like a horizontal asymptote, and any line I draw, we only have one intersection. So since those all only have one intersection, the inverse, it is a function. Okay, so what the horizontal line test allows for you to do is take the shortcut of looking at that horizontal line test as opposed to graphing your inverse and then looking to see if it passes your vertical line test. Okay, so big things for this, how to write an inverse like what we did at the beginning, how to check it by using your composition of your original and your inverse, and then also what does that mean for your graph. So as you're looking at these, always think about what does the equation mean for me algebraically, but also what does it look like graphically. So think about those relationships as you're doing your work. As always, ask questions if you got them. Thank you.